In this very short lecture, I'm going to tell you about the general linear group over a commutative ring R. It's called the group GL subscript n R. So here we'll take R to be any commutative ring. And denote by M and R the ring of all n by n matrices with entries in R. This is a ring, and GLNR is defined to be the set of those matrices A in M and R such that determinant of A is a unit in R. Now I claim that GLNR is a group under matrix multiplication. We already know that matrix multiplication is associative, and the identity matrix is a unit for matrix multiplication. The only thing we need to know is whether a matrix whose determinant is a unit in R has an inverse or not. But for that, we can use the well-known formula for the inverse of a matrix. It's 1 over determinant A times the matrix whose ijth entry is minus 1 raised to I plus j times determinant of A superscript ji. So let me just explain what this means. So A superscript ji is the submatrix obtained from A by deleting the ith row and jth column. And I'm sure most of you have seen this in your linear algebra course as a formula for the inverse of a matrix. So the only thing that is needed for this formula to work is, so this formula works, you've usually seen it over fields like the real numbers or rational numbers or complex numbers, but the only thing you really need is an associative multiplication in a commutative ring, and you just need that this 1 over determinant of A is defined, and that is why we had to take the determinant of A is a unit in R. So really what you can think of this is as determinant of A inverse, and saying that determinant of A is a unit allows us to write this down. You see that GLNR is a group. Let's look at some examples of matrices in GLNR. So the first is called shear, and it's denoted by Uijx. So this is a matrix which is given by ones all along the diagonal, and here we are assuming that I is not equal to j and x is any element of R. And what you do is you take the ith row and you take the jth column, and in here you put, in the ith row and jth column, you put x. So that is the shear Uijx. And the second kind of element I want to introduce is what I'll call an axis dilation. And this is the element delta IA. Here I belongs to is one of the between 1 to n, and A is any element of R that is a unit. So I'll write R star to denote units of R. So this is the matrix with ones along the diagonal, except in the ith row and ith column, the ith diagonal entry, and there you would put this A. We needed A to be a unit because otherwise the determinant of this is A, and that would not be a unit, and this would not be an element of GLNR. And the third element, which is kind of my favorite, is called the axis transposition. And it is just sigma ij, I is not equal to j, and it is the matrix given by, well, it's basically the identity matrix, except that two diagonal entries, two rows and two columns are disturbed. You take the ith row and the jth row, you take the ith column and the jth column, and there you put zeros along the diagonal and you put 1 in these positions. So in the ijth entry and the jith entry will be 1. This is called an axis transposition. If you're wondering why these names are what they are, you can try to understand what these matrices do when you just look at 2 by 2 real matrices, what these matrices do to the Euclidean plane. And I'll have some more notation that I want to introduce, and that is if X is a matrix in M by N R, then I'm going to say that the ijth entry of X is Xij, Xi star denotes the ith row of X, and X star j denotes the jth column of X. So this ith row of X will be thought of as a row vector, and the jth column of X will be thought of as a column vector. Now I want to think of these very special matrices in GLNR as certain operations on matrices X in Mn by R. So, so these, I'll try to think of these in terms of row and column operations. Okay, so if I take a matrix X and replace it by the matrix X U I J little x, then what am I doing? So what I'm doing is, this ends up being taking the matrix, the ith row, ith column of X, and replacing it by the ith column of X plus X times the jth column of X. So it's a column addition operation. So you take the ith column and add to it a multiple of the jth column. And similarly, if you take X, and so now you would be multiplying it on the left, which means that this Uijx would be an M by M matrix of the type Uijx, and this would correspond to taking the jth row of X and replacing it by the jth row of X plus X times the ith row of X. This is called row addition. So this is what the shears do upon left multiplication and right multiplication. And if you take X goes to X times delta JA, then this is just the same as taking the jth column of X and replacing it by A times the jth column of X. So this is column multiplication. And similarly, if you do it on the left, you will get delta JA times x, and what this will do is this will take the jth row of A and x and replace it by A times the jth row. So this is called row multiplication. And x times sigma ij, so if I take x goes to x times sigma ij, this is just interchange the ith column of x with the jth column of x. So this is the column interchange operation. And finally x goes to sigma ijx is the row interchange operation. We interchange the ith row and the jth row of x. I'm sure most of you have seen these row and column operations before, and they're not very difficult to prove. If you are finding difficult to prove them in general, just try with 2 by 2 matrices at first, and then you'll see the pattern.